Good morning to all of you. I welcome you to lecture number 2 of module 4. In previous lecture, we have discussed about the control characteristics of an HVDC system. To begin with, we started with the desirable features, desirable control features, and then we tried to draw the control characteristics of an HVDC system. We will continue our lecture, so I will write here control characteristics. I am reproducing the control characteristics which we have drawn in the previous lecture. So the control characteristics look like this. This is DC line current ID axis, and this is DC voltage axis VD, ID versus VD. Then this is your rectifier characteristic. Your rectifier operates in constant ignition angle control, CIA. Alpha is not allowed to go beyond alpha max, and alpha max for avoiding large reactive power, the maximum delay angle is 20 to 25 degrees. So alpha greater than alpha max is not possible in this case. And alpha less than alpha min, which is around 5 degrees, is also not allowed in this case by the controller. Now this is the rectifier characteristic, constant ignition angle control characteristic, followed by constant current characteristic, CC. Okay. Similarly, we have inverter characteristic. Inverter characteristic is like this. Inverter has constant extinction angle control, CEA control, and here gamma is maintained constant to avoid the possibility of commutation failure under normal conditions and under faulty conditions. And then this inverter characteristic also has constant current characteristic. So therefore this is your rectifier characteristic. Rectifier characteristic comprises of CIA and CC, and this is the inverter characteristic. It comprises of CEA and CC, and this is the point of intersection, say point A, which signifies the operating point of your HVDC link. So for this case, your HVDC link operates at this point. That means at this point the current through the transmission line or current through the link is this much, and voltage of the link is this much. Okay, if there is drop in the rectifier side voltage, for example, if it drops to this value, then your rectifier characteristic goes down. It becomes like this, and you still have the point of intersection because you have incorporated constant current characteristic also in inverter characteristics. Now your new operating point is B, and in case of B, this is the voltage of the link and this is the current of the link. Fine. Now while generating or drawing these characteristics, we have assumed gamma control for the inverter, and when we go for gamma control means the extinction angle gamma is maintained constant at, say, gamma min. So it is maintained always constant under normal circumstances and under abnormal circumstances also. Whenever there is a fault, gamma is not allowed to go less than gamma min. This avoids the possibility of commutation failure. So therefore in the control logic circuit or in the controller, you have gamma reference gamma, which is maybe around 10 to 15 degrees, and you have gamma actual gamma, and your controller always makes gamma actual follow gamma reference. I mean, you say your gamma reference is 15 degrees. Let us suppose due to fault condition on the inverter side, say inverter side, there is a fault. I mean, inverter voltage has collapsed. Because of collapse or because of drop in the AC side voltage of the inverter, the current in the link increases, and because of increase in the current in the link, U increases. That can be, you can understand with the help of this diagram. This is the commutation voltage of value 3. This is 0, this is pi, this is alpha, and from here to here this is U, and this is your gamma. So what is your gamma plus U? Beta. Now beta is equal to gamma plus U. Fine. Now, as soon as inverter AC side voltage decreases, then ID increases. Because of increase in ID, U increases. And because U increases, gamma decreases. Let us suppose gamma becomes, say, 10 degrees only. So there are high chances of commutation failure because gamma is less than gamma ref, gamma min 15 degrees. So what will your controller do? Controller will act very quickly and it will make gamma very quickly equal to gamma ref. So gamma will again become equal to, before the commutation failure occurs, your controller will make gamma again equal to gamma ref, which is around 15 degrees. And hence under abnormal conditions also, it will avoid the possibility of commutation failure. However, you must remember that even if gamma control is used, I will write here gamma control is also not 100% ideal. Gamma control is also not 100% ideal. There may be certain situations in which case your the possibility of commutation failure may be high. Okay, I will write here there is a substantial amount of risk, of commutation failure. Even with gamma control, there is still substantial amount of risk of commutation failure. Now, the question is, what are the factors which are responsible for occurrence of commutation failure even under gamma control? You see, our load current or DC line current ID, which is same as the value current, it is given by IS3 times cos gamma minus cos beta. And we can write ID is equal to, if you remember, this IS3 is root 3 EM by 2 omega L. This we have already derived this expression while discussing the value currents. So ID is equal to root 3 EM by 2 omega L times cos gamma minus cos beta. So this equation, let us suppose, let inverter side voltage AC voltage fall. When inverter side AC voltage falls, in that case your current ID rises. And ID is given, I will write this equation again, ID is given by root 3 EM by 2 omega L times cos gamma minus cos beta. Now your controller will always, when ID increases, gamma may decrease and gamma may become less than gamma ref, reference gamma, which is gamma minimum, and commutation failure may occur. But what will controller do? It will try to maintain gamma constant equal to gamma ref. So therefore with, see gamma, I will write here gamma is fixed at gamma ref. Okay, it is made always equal to gamma ref. So therefore, for given gamma, ID, EM, omega and L, beta is calculated. You have to calculate beta. Beta is calculated. What will your controller do? For given gamma, because it will try to, even under abnormal conditions, it will try to maintain gamma constant at gamma ref, which is equal to, say, gamma min, to avoid commutation failure. So for under fault conditions, under abnormal conditions, since gamma is fixed, for given gamma, current, ID, EM, omega, L, beta is calculated. Because in this equation you have cos beta. So what you do, when fault occurs, current increases. You know what is the rise in current. So ID, you know what is AC side, inverter AC side voltage. There is a drop in inverter AC side voltage. You know what is new inverter AC side voltage. EM, Omega is 2 pi F, L is the inductance, and gamma, because your controller will try to keep gamma fixed. So therefore you can find cos beta, and from cos beta you can find beta. This is what controller will do. And when controller computes beta, so beta will be kept at such a value that gamma is maintained fixed at gamma is made equal to gamma ref, so as to avoid the possibility of commutation failure. But there are certain situations where this occurrence of commutation failure, even under these circumstances, even under gamma control, may be there. So the first is, I will write here, number one, A, The above computation, I will write here the above computation. Which computation? Computation of beta calculation. I will within brackets write beta calculation is based on reduction of AC side voltage of inverter due to three-phase symmetrical fault. Let us suppose a symmetrical fault has taken place on the AC side of inverter, maybe a temporary short circuit, because of which all the three phases have experienced similar drop in the voltage. That's called symmetrical fault. And because of similar drop in the voltage of all the three phases, that is drop in the AC side voltage, ID increases, and then what will your controller do? What will your control algorithm do? It for given ID, EM, omega, L, and gamma, because it has to keep gamma fixed at gamma ref to avoid commutation failure. It computes beta. So this beta calculation or computation of beta is based on symmetrical fault. But it is not necessary that always there will be a symmetrical fault, and asymmetrical fault may also occur. Like the examples of asymmetrical fault are line-to-line fault or line-to-ground fault. So in case of line-to-line fault or line-to-ground fault, the phase voltage of all the three phases will not drop equally. There will be unsymmetrical or asymmetrical decrease in the voltage of the three phases. And under those circumstances, the calculation of beta, you are making the calculation of beta here. Your controller calculates beta assuming symmetrical fault. That means this decrease in EM, decrease in voltage in all the three phases is assumed to be symmetrical. That is true if symmetrical fault occurs. But if asymmetrical fault like line to ground or line to line fault occurs, then voltage of a particular phase or phases will decrease, but the voltage of other phase, which is healthy phase, will not decrease. So therefore this calculation of beta will be computed wrongly by your controller. And since beta is computed wrongly, so therefore there are high chances of commutation failure, because when beta is computed wrongly, gamma will not be fixed at gamma reference, because beta calculation of beta is wrong. Therefore that will result in commutation failure. So therefore I will write here, for asymmetrical faults, U increases and beta is wrongly calculated or wrongly computed by the controller. The controller calculates or computes beta wrongly, hence resulting in commutation failure. And this wrong calculation of beta will not be able to maintain gamma at gamma reference, and that will definitely result in commutation failure. And when I say asymmetrical faults, within brackets I will write line to ground and line to line faults. Okay, so for asymmetrical faults like line to ground fault and line to line fault, the voltage of all the three phases will not drop symmetrically equally. So therefore the calculation of beta done by your controller is wrong, and wrong calculation will be unable to keep gamma equal to gamma ref, and hence the chances of commutation failure are increased. This is first cause. Second is, if rate of rise of DC line current ID is small. I mean, when a fault occurs, if ID increases slowly, that is rate of rise of ID is small, then there is no problem. It will be taken care of by controller. So controller will take care of this. Okay, but if did by dt, that is rate of rise of current, is fast, okay, wrong, it will cause or it will result in wrong calculation of beta. Again, wrong calculation of beta, and hence commutation failure will occur. When beta is calculated wrongly, commutation failure will occur. So what I mean to say is that if your DC line reactor LD is sufficiently large, you have properly calculated that as soon as inverter side AC voltage decreases, there is rise in the DC line current, ID increases. But if your DC line reactor is not sufficiently large, the rate of rise of current may be high, and with high rate of rise of current, did by dt, your controller again does not respond very quickly, and it makes wrong calculation of beta, and because of wrong calculation of beta, gamma will not be equal to gamma ref, and hence the chances of commutation failure are high. So this may be the second cause of commutation failure, even with gamma control. Third is, I will write here, commutation failure may occur when voltage reduction on inverter AC side takes place just after the firing of a valve. That means as soon as the valve is fired, say valve 1 or valve 2 or valve 3 or any other valve, the moment valve is fired, the inverter side, there may be a situation may arise, the moment a particular valve is fired, the inverter side AC voltage collapses at the same instant of time, and in that case the chances of commutation failure are very, very high. But the probability that the inverter side AC voltage falls the moment a valve is fired, this probability is less. So therefore I will write here, but the probability of this is low. It has low probability as compared to 1 and 2 above. Okay, 1 and 2 means we have already discussed. 1 means asymmetrical fault has occurred, like line to ground fault or line to line fault, and because of this line to line fault or line to ground fault, that is asymmetrical fault, the decrease in voltage in different phases is different, and the beta which is calculated by your controller is based on symmetrical fault. But since asymmetrical fault has occurred, it may calculate or it may compute beta wrongly, and hence it may result in commutation failure. That is reason number 1. And reason number 2 is that rate of rise of current may be large. If the rate at which current rises when fault occurs is fast, okay, it will also result in wrong calculation of beta and hence commutation failure. So that is reason number 2. The probability of reason number 3 is very, very low. So therefore reason number 1 and reason number 2 may be mainly responsible for commutation failure even under strict gamma control conditions. So how to avoid this probability of commutation failure? So therefore we can say that it is not sufficient only to compute EM and ID, but in computation process following has to be considered also. So therefore I will write here, therefore it is not sufficient to compute EM and ID only. Following is to be considered. I mean, if you consider the following factors, then the chances of commutation failure are very, very low. Number one, amplitude of commutation voltage. Your controller should calculate the amplitude of, it should know the amplitude of commutation voltage. Amplitude of commutation voltage. Not only amplitude of commutation voltage, but also the phase of commutation voltage. Phase of commutation voltage. Third is magnitude of DC line current. Magnitude of DC line current ID. This your controller should know this also, and also it should very accurately know the rate of change of DC current. DC line current. That is, it should accurately know did by dt. Therefore, even if your di by dt is very fast, since your controller accurately knows the rate of rise of current or change in the current, it will very quickly act, and the chances of commutation failure are reduced. So therefore, if your controller, in addition to computing EM, I, omega, L, etc., it also knows the amplitude of commutation voltage. It accurately knows the phase of commutation voltage. It knows the magnitude of DC line current when a fault occurs, and it also knows the rate of change of or rate of rise of DC line current, d by dt. So in the computations, all these factors are taken into consideration, and chances of commutation failure are avoided. So therefore, in the control of HVDC link, your controller, inverter side controller works on gamma control. And the aim is that in gamma control, gamma will be always maintained at gamma reference, which is the minimum gamma. And even under fault conditions, gamma will not be allowed to go below gamma ref to avoid commutation failure. With above considerations, these four considerations, your controller will almost perfectly work, and it will always, even under severe fault conditions, it will try to avoid the probability of occurrence of commutation failure. So that is about this. Now after this, we will try to develop the control characteristics for power reversal. I will write here control characteristics for power reversal. Power reversal. You know the control characteristics for, power reversal means, if this is your HVDC system, this is rectifier side R, this is LD, ID, and this is your inverter side I. Generally, power flows from rectifier side to inverter side. But in case of back-to-back, link, your inverter may behave as rectifier and rectifier may behave as inverter. In that case, direction of power flow will reverse. Power will flow from this converting station to this converting station. So in that case, what will happen to your control characteristics? Let us see control characteristics under such a situation. So this is ID and this is VD. Let us first of all reproduce control characteristic for positive direction of power flow. For positive direction of power flow, this is your rectifier control characteristic. It comprises of constant ignition angle control and constant current control. And your inverter characteristic is like this. Inverter, it comprises of constant extinction angle control, CEA, and also constant current control. And this current, this current is called current margin, ID margin. Okay, so this is the control characteristic for positive flow of power, P. That means if P flows from this station to, say, P flows from this converting station to this converting station. That's what I am showing. Now, if the direction of power flow reverses, say P now flows from this converting station to this converting station in this direction, what will happen to your control characteristics? Your rectifier will behave as inverter and inverter will behave as rectifier. So therefore, your rectifier characteristics will become inverter characteristics and your inverter characteristics will become rectifier characteristics. So therefore, if you take these characteristics down, so This was a rectifier characteristic because for this direction of power flow, this converter was acting as a rectifier. And for this direction of power flow, now this converter has to act as an inverter. So therefore, these were the rectifier characteristics in positive flow of power. For negative flow of power, that means if power flows in this direction, now this rectifier characteristic will become inverter characteristic. So I can show you. So it becomes inverter characteristic with constant extinction angle control and constant current control. And what will happen to your inverter characteristics? They will become rectifier characteristics because your inverter now behaves as a rectifier. For this direction of power flow, your inverter behaves as rectifier. So therefore, inverter characteristics will now become rectifier characteristics. Let me show you. These were the inverter characteristics for this direction of power flow. And now for this direction of power flow, your inverter characteristics will become rectifier characteristics. So rectifier means constant ignition angle control and constant current control. So therefore, for this direction of power flow, if power is flowing from this station to this station, in that case, this converter behaves as a rectifier and this converter behaves as inverter. So in that case, the rectifier characteristic is like this, CIA and CC, and inverter characteristic is CEA and CC. And when the direction of power flow reverses, power now flows from this converting station to this converting station. Now this converter will behave in the rectification mode and this converter will behave as in the inversion mode. So therefore their characteristics will now reverse. The rectifier characteristics will now become inverter characteristics, CEA and CC, and inverter characteristics for reverse direction of power flow will become rectifier characteristics, CIA and CC. But the problem is that, see, for this direction of power flow, this is the operating point, say P, because the point of intersection of inverter and rectifier characteristics is the operating characteristics of HVDC link. So for positive direction of power flow, this is the operating point. What is the operating point for negative direction of power flow? There is no operating point because inverter characteristic and rectifier characteristic are not intersecting each other. So therefore, since there is no point of intersection, since there is no point of intersection, so there is no operating point. So therefore, how to get the operating point? You can get operating point if you if your inverter current becomes for inversion mode, I mean for direction of power flow, if inverter current becomes stronger than rectifier current. For this direction of power flow, that means power flowing from this station to this station, you can see rectifier current is greater than inverter current. Now if you, for direction of power flow, that means if power flows from this converting station to this converting station, the operating point will be there when there is point of intersection between the two characteristics. So what you have to do, your inverter current has to be higher than rectifier current. So therefore your characteristics for reverse power reversal will get modified like this. Let me show you. So again, this is ID and this is VD. This is your rectifier characteristic comprising of CIA and CC. And this is the inverter characteristic. Inverter characteristic comprising of CEA and CC for this direction of power flow. So for reverse direction of, I am drawing these characteristics for reverse direction of power flow. For reverse direction of power flow, your rectifier characteristic will become inverter and inverter will become rectifier. So this will be now your inverter characteristic I, CEA and CC, and this will become the this is inverter characteristic, and here it will become rectifier characteristic R, CIA and CC. Now you can see there is now point of intersection. Let us call this point of intersection as P dash. So P dash is point of intersection between rectifier characteristic and inverter characteristic for reverse direction of power flow, and is the operating point. It represents the operating point. So therefore your HVDC link will operate at this point. Corresponding to this point, this is the current in the link and this is the voltage in the link, negative voltage, because your this converter is now operating in inversion mode and this converter is operating in rectification mode. So polarity of voltage has reversed. Current direction remains same, positive, but the polarity of voltage is reversed. Okay, so how was this possible? How was it possible to get the operating point for the reverse direction of power flow when we have swapped the currents of rectifier and inverter? I mean, in this direction of power flow, the rectifier current is higher than inverter current, and when your HVDC link operates in this, in fourth quadrant, I mean when power flow direction reverses, your inverter current, you can see, is now higher than rectifier current. Here rectifier current is higher than inverter current. Here inverter current is higher than rectifier current. So therefore this operating point we have obtained by swapping the current CC characteristics of rectifier and inverter. So this, I will note down here, this operating point is obtained by swapping the constant current characteristics of rectifier and inverter for reverse power flow. So therefore your controller will act like this. When direction of power flow is positive, I mean power is flowing from this converting station to this converting station, this converter is operating in the rectification mode and this converter is operating in the inversion mode. So these are the characteristics. This is rectifier characteristic, this is inverter characteristic, this is point of intersection, and this is the operating point. And when the direction of power flow reverses, that means power is flowing in this direction from this converting station to this converting station. Now this converter will operate in the rectification mode and this converter will operate in the inversion mode. And to get the point of intersection, you have to swap the CC characteristics of rectifier and inverter. That means the inverter current is made now higher than rectifier current, and you get the point of intersection P dash, and this gives the point of intersection for power flow reversal. So this is obtained only when we have swapped CC characteristics of converter, rectifier and inverter. Okay, so this is how we obtain the operating point for this direction of power flow and operating point for reverse direction of power flow. So this is about control characteristics for power reversal. So therefore our control characteristics get modified for from rectification from one direction of power flow to another direction of power flow. Now you have to make some more corrections in your inverter characteristics. So let us see what are the other corrections we have to make in inverter characteristics. Corrections, I will write here corrections in control characteristics. Some more corrections have to be made in control characteristics to accommodate other things also, other abnormalities also. Okay, one of the modification is like this. Let us again draw the control characteristics. This is ID and this is VD for this direction of power flow. P is in this direction. So this is your rectifier characteristic R with constant ignition angle CIA control and constant current controls. Let us suppose normally inverter characteristic would be like this and like this. Okay, inverter will have less slope, but let us suppose that there is some fault on the inverter side. The inverter side AC voltage has reduced. So I will write here, due to fault, the inverter side AC voltage reduces, and because of that we know that current increases, and because of increase in current U increases. Okay, and when U increases in the electrical equivalent circuit, how is taken care of? How does that electrical equivalent circuit take care of increased U? Because of increase in U, you have seen in 2 and 3 value conduction, when U increases, there is loss of voltage. You have got the mathematical expression for converter average output voltage also. More U, more is the loss of voltage, converter average output voltage. So in the electrical equivalent circuit, this is taken care of by RCI, that's electrical, equivalent commutation resistance. Now we know that inverter output voltage VDI is equal to VDOI cos gamma minus RCI into ID. Now since because of collapse or decrease in the inverter side AC voltage due to some fault, ID has increased. Because of increase in ID, U has increased, and in the electrical equivalent circuit, RCI, equivalent commutation resistance has increased. So therefore, what happens to inverter output voltage? The output voltage on the inverter side is, inverter average output voltage minus this drop. Okay, since RCI has increased due to increase in U. In the electrical equivalent circuit, this increase in U is taken care of by increase in RCI. Since RCI has increased, so this drop increases. So therefore, what happens to the slope of inverter voltage? Inverter voltage becomes more slopey in nature. So therefore, your inverter voltage will become slopey like this. Let us suppose its slope increases. So this is the slope of inverter voltage. So your inverter characteristic comprises of constant extinction angle, CEA, and constant current. But what is the difference of this characteristic and normal inverter characteristic? Normal inverter characteristic would have been like this, very small slope, less than the slope of rectifier characteristic. But because of AC side voltage decrease, ID has increased, that has increased U, and that has increased equivalently in the electrical equivalent circuit, that has increased equivalent commutation resistance. And because of increase in equivalent commutation resistance, this drop increases, so this voltage decreases. So now that means the inverter voltage characteristic will be more slopey, more drooping in nature, as you can see. Now what is the problem with this? Okay, this is the operating point. Let us suppose operating point is P. Now let us assume after some time rectifier voltage also collapses. There is decrease in the rectifier side voltage. Okay, now because of the decrease in rectifier side voltage, let me show you. Let me draw this this characteristic again for more clarity. This is ID, this is VD, this is rectifier side, characteristic CIA and CC. This is inverter side characteristic. Inverter side characteristic has large droop. This is CEA, CEA, and CC. Now let us suppose rectifier side voltage has decreased. I mean, there is decrease in rectifier side voltage, and your new rectifier characteristic becomes like this. Earlier this was your rectifier voltage, and now due to fault or due to sag on the rectifier side, let us suppose rectifier side voltage has reduced. Now when rectifier side voltage is reduced, the problem because of high slope of inverter characteristic, this is inverter characteristic I, because of large slope of inverter characteristic, this rectifier characteristic intersects the inverter. This is now your new rectifier characteristic because of drop in the rectifier side voltage, and this is the inverter characteristic. The rectifier characteristic and the inverter they intersect at 3 different points. This is small a, this is point B, and this is point C. There are 3 points of intersection. See it very, just check it very keenly. Okay, see it very closely. This is this was the earlier rectifier side characteristic, and this was inverter characteristic. Because of fault on the inverter side, it became more drooping in nature, more slopey in nature. But point of intersection is still this. Now suppose due to some fault, if a rectifier characteristic also drops, it drops from this to this. Now because of high slope, large slope, or more drooping nature of inverter characteristic, there are 3 points of intersection between rectifier characteristic and inverter characteristic. Now your new rectifier characteristic is not this, it is this. And this is your inverter characteristic. Now you can see your rectifier characteristic intersects inverter characteristic at point A, then at point B, and then when it comes down at C. So therefore, due to drooping nature of inverter characteristic, due to drooping nature of inverter characteristic, there are now 3 points of intersection. There are now 3 points of intersection between rectifier and inverter characteristics. What are those 3 points? A, B, and C. So therefore, at what point will your HVDC link operate? It will operate at no point. Sometimes it will try to operate at point A, and immediately it will hunt for point B, and then it will hunt for point C. So therefore, for some time it will operate at point A, then for some time point B, point C, and then it will keep on hunting for one operating point. So therefore, your controller hunts for stable operating point, and it will not get that operating point, and it will keep on hunting, but it will not get that stable operating point. So this means your controller becomes unstable, your controller, and hence your HVDC link becomes unstable. So this leads to instability of your HVDC link. So this is the problem with normal characteristics. So how to take care of this? In order to take care of this, the inverter side characteristics have to be modified. So to address this issue, inverter characteristic is modified either with constant voltage control, or constant beta control. If you go for constant voltage control is generally not used because it worsens power factor. It deteriorates power factor. It will solve this problem, but it will deteriorate power factor. Therefore, we go for constant beta control. How this constant beta control solves your problem? Let us see. Now, therefore, modified control characteristics will be like this. Modified control characteristics will be like this. See, this is your control characteristics. This is ID, this is VD, this is rectifier characteristic comprising of CIA and CC, and this is inverter characteristic. Now we will again assume inverter characteristic has become slopey because of drop in the inverter side voltage. This is inverter characteristic CEA, and then what we do is from here to here we introduce C beta control. C beta control means constant beta control, and then constant current control. So what is this characteristic? This is constant beta control. Your controller maintains during this period, when inverter characteristic becomes slopey, it maintains this beta constant, and because of maintaining beta constant, your characteristic, which previously was like this, which was becoming very, very drooping, which was like this, okay, it gets modified. It gets modified like this. This part of characteristic is called constant beta control or constant beta characteristic. And because of this, when your rectifier side voltage decreases, it will have only one. Say your rectifier side voltage has fallen, it has only one point of intersection. Whereas here, when rectifier side voltage was falling, it was having 3 points of intersection, A, B, and C. And therefore, your link was not operating stably. It was hunting for a stable operation, but it was never getting that stability. Here, with modifying the inverter characteristic, converting this part of characteristic into constant beta control, you have only one point of intersection. So therefore your HVDC link will operate stably. This is for this direction of power flow. For opposite direction of power flow, it will be like this. See, this is ID, this is again VD. So it will be like this. This is rectifier characteristic CIA plus CC, and this is inverter characteristic. Here also you convert it into beta. This is beta control, this is constant current control, and this is inverter control CEA. Here also you don't go like this, so you have beta control. So therefore this is for this direction of power flow. For this direction of power flow, we already know that inverter current becomes more than rectifier current. For this direction of power flow, rectifier current is more than inverter current. But this constant beta is introduced for this direction of power flow. It is introduced for this direction of power flow also. This is how we modify the control characteristics of an HVDC link, and modify it by adding constant beta. It's not beta C, it is C beta, constant beta characteristic into it to take care of inverter side AC voltage collapse, and hence to get only one operating point. So what are the other corrections or other considerations apart from introducing constant beta control? What are the other considerations? Other considerations are always voltage controller or current controller is used. Always voltage controllers or current controllers are used instead of DC power control. We don't use DC power control, we use constant voltage control or constant current control because of the following reasons. Number one, the transmission line resistance is very, very small. The transmission line resistance RL is very small. It may be 0.1 ohm, 0.2 ohm, something like that, very small. So therefore, this results in small damping factor. Since transmission line resistance is very, very small, it results in smaller damping factor. Smaller the transmission line resistance, smaller is the damping factor. And smaller the damping factor, okay, more huge oscillations will be there. Huge power oscillations will be there. Huge power oscillations. And because of huge power oscillations, the DC transmission line operation will become unstable. I will write here unstable operation. So I repeat, if instead of current control or voltage control, you go for power control will result in unstable operation. Why? Because transmission line resistance RL is very, very small. That means line has very small damping factor, and small damping factor, whenever you want power flow control, of the HVDC link, since transmission line resistance is small, it has small damping factor, there will be always huge power oscillations. Whenever you try to alter the power in the DC line, control the power in the DC line, it will result in huge power oscillations and hence unstable operation. So therefore, instead of DC power controller, we go for either voltage controller or current controller. This is one consideration. Another consideration is, we know that DC power is given VD into ID, right? So you can control DC power if instead of using voltage control or current control, you use power control. This power can be controlled independently by controlling either voltage or current, or by simultaneously controlling voltage and current. And therefore, this will make your controller very complex. Controller becomes complex and loses flexibility. It loses flexibility. So there, because you have to, for controlling the, since instead of voltage control or current control, you are using the power control, and power can be controlled by either controlling DC line voltage or DC line current or both. So if you control power this way, by controlling voltage or current or both of them, the controller will become very complex and your controller will lose flexibility. So therefore power control is not used because of this reason also. Third reason is, I will write here, a strong communication link is required. A strong communication link is required between both sides for better control. That means if you go for power control instead of voltage control or current control, for better power control, you need a strong communication link between the two converting stations. And it is possible that your converting stations may be hundreds or thousands of kilometers away from each other. And then it will be very difficult to maintain this strong communication link between the two sides. So this is another problem. And last of all, since PD is equal to VD into ID, if voltage on rectifier side or inverter side falls, so I will write here for low voltage, to maintain the power constant, PD is equal to VD into ID. If voltage falls substantially, your link will try to increase the current to maintain the power constant in the link. Because when we say power control, the power control means power in the link has to be maintained constant. And if there is a collapse in the link voltage due to some fault, then your control will automatically increase current, so that VD into ID becomes equal to PD reference. Okay, and that is a problem. If ID is increased by a large percentage, then this ID has to flow through line and it has to flow through converter valves, and it will result in instant damage of converter valves. So damage of valves, that means damage of converters due to high ID. So therefore we never go for power flow control, we go for voltage control or current control. Generally current is maintained constant, so practical way is to go for voltage control of HVDC link instead of current control. Power control is not used because of these drawbacks which I have discussed. So generally we go for voltage control. And now you further need modification in the characteristics. So you have to incorporate, I will write here, incorporating VD call, voltage dependent current order limit, in control characteristics. Okay, VD call means V stands for voltage, D stands for dependent, C stands for current, O stands for order, and L stands for limit. Voltage dependent current order limit, VD call. So let me first of all draw and incorporate this VD call, and then I will explain. I have to incorporate this VD call in control characteristics. So my control characteristics will get further modified as like this. This is rectifier characteristic with CIA and CC. This is CC, and then this is VD call. This is inverter characteristic with CEA, and then constant beta control, C beta, CC, and then VD call. Okay, so what is done, actually what happens, sometimes your DC link voltage collapses because of some fault. It is possible that this DC link voltage has collapsed. It has further collapsed it has further collapsed, it has further collapsed, suppose it has collapsed to extremely low voltages. If you see the normal operating conditions, I mean, if you have this type of operating conditions, in which case the voltage collapses, the link voltage collapses, then for making certain amount of power to flow, current in the link has to increase. Because link voltage has collapsed, your controller will automatically try to increase the current to maintain some amount of power. Otherwise, what will happen under extremely low voltage conditions? There may be almost no power in the link. It will be very difficult to maintain or to keep some power flowing in the link. So to keep some power flowing in the link, under extremely low voltage conditions, your controller will try to increase the current. Because voltage has decreased, current it will try to increase to maintain some amount of power in the link. But as soon as it tries to increase the current to maintain some power in the link, it may so happen that current may go dangerously to excessively large values, and that will cause puncture or damage of the valves of the converter, and both the converters will get damaged. Converters at both the stations may get damaged. Okay, so to avoid that possibility, under extremely low voltage conditions, what is done? Some limit on the current is kept. You see here, for this is the rectifier, characteristic. Under normal operation, it tries to maintain the current constant, but under extremely low voltage conditions, it puts some limit on the current. So what happens? See, if your voltage goes on decreasing, the current also, it does not keep very high. The current also, it decreases the current, and under extremely low voltage conditions, it even makes current zero, and hence link becomes inoperative. Similarly, in the inverter characteristic, this is CEA, this is C beta, and then this is CC. Under extremely low voltage conditions, you can see it decreases the link current. Okay, so therefore your controller puts, I will write here, controller puts some limit on line current to avoid damage. And this is called VD call. This is called voltage dependent current order limit. This is normal current order for rectifier, and this is normal current order for inverter. But under extremely low voltage conditions, the current order gets changed. This is the current order. This is how it changes for rectifier, and this is the current order which is changing for inverter. And since this current order depends upon the voltage, so it is dependent upon the voltage. If voltage is high, your current order may be high. If voltage falls, it collapses quickly to very low values, the current order also decreases. So this is called voltage dependent current order limit. So therefore your final control characteristics are like this. So therefore when you see the final control characteristics, your final control characteristics will have rectifier characteristics and inverter characteristics. So your rectifier characteristic, you can see it comprises of CIA, CC and VD call. CIA, constant ignition angle control, constant current control, and VD call, voltage dependent current order limit. Remember, this VD call is applicable only for extremely low link voltage, extremely low voltage conditions. And what about your inverter? Your inverter characteristics comprise of CEA, constant extinction angle control, constant beta control, constant current control, and VD call. CEA, C beta, constant beta, CC, and VD call. So this is the final VI characteristic or final control characteristics of your HVDC link. Okay. So that completes our discussions on control characteristics. We have started in previous lecture with a simple control characteristic, and then with with more and more complexities and more considerations in the system. We kept on changing the control characteristics till finally we got the final control characteristics of HVDC link. That is this. Rectifier characteristic comprises of CIA, CC, and VD call. Inverter characteristics comprise of CEA, C beta, CC, and VD call. So these are the final control characteristics. Now let us discuss now with the help of a block diagram about controller design. when we design the controller, what is the philosophy of controller design? Controller design philosophy, or I will write hierarchy. Controller design hierarchy. That will be clear with the help of this block diagram. This is our system. Let me first of all draw, then I will try to explain it. This is system control. System control gives rise to reference power. This is called power order reference. And then you have master control. This is master control. And this master control has communication to a remote terminal. This master controller gives us IREF, which is called current order, reference current or current order. And once you know this IREF, you have now value groups. You have pole 1, you have pole 2. This is pole 1 control. And on this side you have pole 2 control. This is pole 2 control. Whether it is pole 1 control or pole 2 control, the control is further divided into two hierarchies: VGC, value group control, VGC, value group control. And similarly on this side you have VGC and VGC. VGC means value group control. Value group control. So what is the hierarchy? The hierarchy is, first of all, you have system control, and you want to know what is the power in your HVDC link. So that gives you PREF, power order. And now we don't go for power control, we go for current control, okay, or voltage control. Then this master controller converts this power ref into reference current. This is our reference current. Now you have two converters. You have pole 1 converter, you have pole 2 converter, you have two converters. You have to control the two converters. And value group controllers will control your converters of this pole and converters of this pole. This is the hierarchy of your controller design. So whenever you design controller, you first of all see what is the total power to be carried by HVDC power transmission line, total power in the line. From that you find ID reference, and then from once you know ID reference, then you go for converter controls using value group control. Okay. And now finally I will show you the schematic diagram of controller. Controller schematic diagram. Schematic diagram. Okay, now your converter has two parts. It has this side is rectifier and this side is inverter. Like for example, this may act as a rectifier, LD, ID, and this side may act as an inverter. In fact, on rectifier side as well as inverter side, you have phase control converters. So you have to control two converters. You have to control this pole converter as well as this pole converter also you have to control. So as far as this pole controller is concerned, you have to go for constant ignition angle control for this, that is alpha control. And for this you have to go for constant extinction angle control, that is gamma control. So inverter has gamma control and rectifier has alpha control. Let us see how we can achieve these two. So the schematic block diagram is like this. We have gamma measuring circuit. Gamma measuring circuit, I will write here. Let me first of all draw, then I will explain it. This is your gamma ref, reference gamma. This is gamma, okay, and then this is minus, this is gamma ref, reference gamma, and there may be some disturbance also. I will write here disturbing magnitude. Some disturbance may get added to it, disturbing magnitude. and then this is given to gamma controller, and then you have this selector. You have this selector, and the controller, gamma controller output is VC1, control voltage VC1. So then you have another controller here. This is reference DC reference current ID ref, and this is actual DC current ID, and it is on the rectifier side we try to maintain this ID at ID ref, and then this is your switch S. I will write here ID margin, and you have ID controller, DC reference or current controller. Just like you have gamma controller, you have ID controller, and this is VC2. Okay, so now VC1 and VC2 gives VC, control voltage, total control voltage, and then this is your firing angle control block. Okay, and it generates the delay pulses with delay angle. It decides what should be the delay angle. Okay, this FAC is firing angle control block, firing angle or delay angle control. Now this is your rectifier control, R, and this is inverter control, I. So now you have two types of controllers. One is gamma control. On inverter you have gamma control, and on rectifier you have current control. Okay. Now on the rectifier side, we actually try to maintain the DC line current as constant. So let us suppose DC line current reference value is ID ref, and this is the actual DC line current. If actual DC line current is not equal to reference DC line current, then an error will be produced here that will be given to ID controller, which is basically a PI controller, and then it will go to this block. This block will generate some control voltage VC, which will go to firing angle controller, and at the output of firing angle control, you will get control pulses to various valves of the rectifier converter, at a certain delay angle alpha. So it will decide what should be the delay angle. It will manipulate, or it will control or change the delay angle in such a way that this ID under all circumstances becomes equal to ID ref. We have studied yesterday some situations when rectifier side voltage increases, when rectifier side voltage decreases, or inverter side voltage increases or inverter side voltage decreases. Under those circumstances, how rectifier controller acts very quickly. It tries to manipulate, or it tries to adjust this delay angle of rectifier in such a way that ID is again made equal to ID ref. Okay. That is electronic control. If electronic control fails, then there is online tap changing transformer also that aids in maintaining ID equal to ID ref. So this is about rectifier control. It is very simple. Actual DC line current is compared with reference DC line current, and any error is given to PI controller, and that adjusts the value of control voltage, which is given to firing angle control, and firing angle control generates the firing pulses for valves of the converter, and adjusting the delay angle in such a way that ID always remains equal to ID ref, even under normal conditions as well as under fault conditions. This is the rectifier side control. What about inverter side control? What is the control objective in inverter side? On the inverter side, our gamma should be, we try to maintain gamma constant. On rectifier side, we try to maintain DC line current constant equal to ID ref. On inverter side, we try to maintain gamma equal to gamma ref, which is equal to, say, gamma min 10 to 15 degrees, so that commutation failure is avoided. Okay. How do you get this gamma? Gamma is basically an angle, and it is very difficult to find that angle. You need a special algorithm for that. So you need gamma measuring circuit, which is implemented through an algorithm. What will this gamma measuring circuit do? It will implement an algorithm which will at all the time measure gamma, and it gives that gamma to this comparator. and this gamma is compared with gamma ref. If gamma is not equal to gamma ref, say some fault has occurred on the inverter side AC voltage has fallen, so what will happen to gamma? Gamma will increase, but it has to be always equal to gamma ref. If gamma becomes more than gamma ref, an error is produced which goes to gamma controller, which is again a PI controller, and it generates the control voltage VC1 in such a way that VC is manipulated, and then beta or beta of or alpha of inverter side converter is adjusted in such a way that this gamma always it comes back and it becomes equal to gamma ref, so it avoids the commutation failure. So this is rectifier side control and this is inverter side control. So that is all about HVDC control characteristics and a simplified block diagram I have shown here for rectifier control as well as inverter control. This is a concise block diagram. This is not the detailed block diagram. If you draw the detailed block diagram, then many blocks may get added to it, and it will not be so simple. It will be a little bit complex. Okay, on rectifier side, the aim of rectifier is to maintain DC line current at reference current, and the aim of inverter is to maintain gamma at gamma ref to avoid commutation failure. And then accordingly alpha is adjusted in such a way that both the objectives on rectifier side as well as inverter side, both the objectives are fulfilled. On rectifier side, the objective is ID should be maintained constant at ID ref, and for inverter the objective is that gamma should be maintained constant at gamma ref, even under normal as well as fault conditions also, to avoid commutation failure. So with this I will end my today's lecture. I advise you to go through this lecture. In case of any difficulty, you can discuss with me, and inshallah in our next lecture we will study some firing angle schemes for HVDC power converters, and hopefully in our next lecture we will try to finish this module. So that will end module number 4, and then we are left with last module, module number 5, that is harmonics and harmonic filters. Thank you.